Look at this proposition. See this proposition. You can see the statement. This proposition is very important in the 4th unit of measure and integration. Okay, this is the proof is very simple. Okay, you may learn so many named theorems, difficult theorems, but you ignore these kind of theorems because they are very easy. You may feel they don't ask you in the examination, but they asked this proposition for a university examination. Okay, one time asked, more than one time asked question. Okay, I saw this question in 1 or 2 question papers previous year. So here you are having the statement f be a measurable function on E. You are having a measurable set E. Within that measurable set E, you are having a measurable function, that is f. Then f plus and f minus are integrable over E. Okay, if and only if mod f is integrable over E. If this is integrable, these two are integrable, this will be integrable. If this is integrable, these two are integrable. Okay, this is what the proposition is, and if and only if. So you know that you will have 2 parts in the proof. Okay, so first part and this is the converse part. Okay, the first part you are assuming mod f is integrable over E to prove this. No difficulties. You know that mod f is integrable over E, no, in the assumption. So by the definition of integrable, you can write like this. Okay, integral this mod f over E less than infinity. By the definition of integrable, you are writing this. Now we have this, that is f plus will be lies between. You have to prove f plus and f minus. No, so you have to write what is f plus and what is f minus. So that is why you are usually you will have f plus in between 0 and mod f. F minus will be present. F minus also will be present between 0 and mod f. Okay, so that is what you are writing. You are having f plus between these two, and you are having f minus between these two. You are writing that. You are writing. So now what you are doing, you are taking integral, comparing to these two terms. This is 0, no? So you are ignoring. To these two values, you are taking integration, so that you are getting this. You know that this value is less than infinitive from the assumption. So you are putting less than infinitive. Similarly, you are writing for this also. So from this, comparing this and this, you will get this, and comparing these two, you will get this. So look at this. By the definition of integrable, you proved it, no? So by the definition of integrable, from this you can say this f plus and f minus are integrable. Is that okay? Now let's see the converse part. Converse part, you are assuming f plus. The converse part, what you will do? You have to assume what you have proved in the previous one, right? You are assuming f plus and f minus are integrable. To prove mod f is integrable. So to prove that, from the assumption you can write these two, no? Because you are having f plus is integrable, f minus is integrable. So by the definition of integrable, you can write these two. Now we have this result. Mod f equal to f plus plus f minus. You are having this result from the definition. Mod f equal to this value. Okay. So you are writing that. After that, you are taking integral over E, so that you integral to all the terms. So you will get this. You know that this value, this is less than infinitive, this is less than infinitive. So in total, even when you add these two, you are going to get less than infinitive. Finite value. Less than infinitive means what? It is finite. That is what the meaning. Okay. So if this is less than infinitive, that is, this is finite and this is finite, then when you add these two finite values, you are going to get a finite value. So that is what the meaning. So from this you can say, comparing these two, you can write this. So therefore you can say, from this you can say, from the definition of integrable, mod f is integrable. Very easy proposition, no? Okay, ignore the background sound. Okay, sorry.